Oh no, boys and girls, why are we doing this?
How did I get here?
Oh God. Anyway, okay, James. Speed of light. Scott, go.
Okay, James, you expressed that you did not understand or whatever the concept of the two-way speed of light.
Yeah, it made no sense to me at all. Nerdy Rodent tried to explain it to me like 3 or 4 different ways, and each time I got more confused.
Well, let's do a thought experiment, and you can see. Can you see the diagram?
I can see it.
That amazing work of art. This is a very high-powered flashlight, and this is a reflecting mirror. And we're just going to pretend I didn't know how to draw a clock or whatever very efficiently, so I left it out. But there's also a timepiece on the same side as the flashlight. And essentially the only way that we've been able to measure the speed of light with, anything like a direct observation is doing this method of shining a light, bouncing it off the mirror, and measuring the total time it took the beam of light to travel to the mirror, bounce off, and come back. So that's 2 ways. That's 2 directions, out and back. Now, let's say the mirror is placed 186,282 miles away, which sounds like a strange and arbitrary number, but it really makes the math come out easy. So you click your flashlight, the light beam travels out, and then it travels back. And it, with your little measurer device, it takes
2 seconds.
2 seconds. I'm trying to get over to the 2 seconds. And how far has it gone? It's gone whatever 186,282 miles times 2 is, and that's, oh gosh, I hope I can just do select all, copy, and I'm going to paste that. Hopefully it will paste, but I'm just going to not worry about writing it down. It's 372,000 some odd miles in total. Well, how do you calculate velocity? It's the total distance traveled, but divided by the total time, and you get miles per hour or miles per second in this case. You following me so far?
I sure do, yep.
Okay, so it took 2 seconds to do a round trip of 300, I forget what we said, 72,000. I'm just going to say
Windows has got a calculator built in.
Yeah, I know. I'm looking at it, but this is a paint thing, and I don't know if you can actually put the number there. But if you take that 382,000 some odd and divide it by 2, you get back to 186,282 miles per second, which is the speed of light. But it's not the directly observed speed of light. In one sense it is, but in the other sense, it's actually the average of the round trip.
Yep.
2 directions. So there's the speed with which it goes out, and there's the speed with which it comes in. But because you can only do it with that bidirectional method, it comes out to 186,282 miles per second on average. Now, it would seem like, hey, that settles it. We've many times we've settled what the speed of light is, but there's an assumption in the background of that. It's a pretty good assumption. There's really no reason to assume it's any different. How do we know that beam of light didn't take 1 second to get out to the mirror? I'm sorry, 2 seconds to get out to the mirror and returned instantaneously in zero amount of seconds back to the flashlight. The average would come out the same. It would have gone a total of 382,000 whatever, and traveled for 2 total seconds. Or it could have gone out instantaneously and come back in 2 seconds, or some mix.
Sure.
Therein, okay.
Sure.
Well, it seems kind of trivial. You know, it's by convention, we assume that the light beam is traveling at the same speed in either direction because it makes everything easier. You can do all the same calculations and come to the same conclusions in physics, I believe. If Leo is actually listening, he might have something to say about that. But you could come to the same conclusions. You know, assuming it was instantaneous one direction and takes the full 2 seconds coming back or whatever, or some mixture. But it really makes our mathematics a lot easier in order to do our calculations, eliminate all sorts of stuff that's going to get divided out anyway. So anyway, but what has happened is in the world of young Earth creationism or intelligent design, I think his last name is Lyle. I can't remember his first name because it's been a little while since anybody's referred to him. But he said, in answer to what is known as the starlight problem, and of course that's the problem that the Earth was created in 4004 BC, but the age must be older because the starlight out there takes hundreds of thousands of years in many cases to travel to us, and or tens of thousands of years to travel to us. So how can we have a 6,000-year-old universe and have starlight coming to us at some point, apparently, with the appearance of age? Some people, have said that, the universe was created with the starlight, 4,000 light years away to give it the appearance of that age. But Lyle, this intelligent design astronomer, came up and just said, hey, why don't we, instead of assuming it's the same either direction, the same speed either direction, let's assume that it's instantaneous in one direction and then takes twice as long in the other direction. We can't tell. There's nothing to say that it's false. There's nothing to say that it's true. So if I want to, I can solve all of this by coming up with a different assumption about the speed of light, and that's the whole controversy. Is that the only way to measure the speed of light is through this two-way method, and taking the average, but because you can't, and the reason why you can't do it any other way is you have a sensor. I don't know. It's just you can't measure it any other way.
Okay, like for instance, if you put somebody on the moon and they had one sensor and somebody on Earth, and they fired the light off, right? And then they sent a radio message at the same time from the Earth to the moon to tell you when they fired it. Well, the radio message is going to go at the speed of light too. So how the fuck does that work? So there's no, so you have to measure the average, because they set up the equipment so that they know exactly when the light went and when it returns at one sensor. So we always have to measure the average. But the question is, why would the speed of light, like, okay, you turn the flashlight on and the photons shoot out of your flashlight, and then they see that, oh, I got to do laundry. So they stop at the laundry room and they get distracted. No, photons don't have ADHD. There's absolutely no reason for them to travel at a different speed than and besides, the speed of light, because of relativity, turns out to be a constant because of just the very nature of space time. And I don't know where the hell Lyle, how he's getting around all that, but and that's about as much about the physics that I know. But anyway, you see that we have to measure the average, and they're saying, oh, well, we don't know if it, goes and does the laundry and maybe makes itself a cup of coffee and then it continues on its journey, right? Or we don't know if it's really, really quick like a bunny on coming from stars, but then going, the other way, it slows down like a fucking turtle. It's just fucking ridiculous. What they're doing is they're trying to come up with some kind of bullshit to account for this 6,000-year-old Earth, and it just doesn't fucking work. It just doesn't.
Okay. What they call this, I finally found the name for it, and Lyle's version of this is the anisotropic synchrony convention model. That's the one that says that the speed of light in the two directions are different from one another. Of course, I guess the convention is actually the one being used is an isotropic synchrony convention, assuming that the speed of light is same both directions.
Yeah. Anyway, okay.
So does this help in any way? Are you still feeling muddled or confused or unsure?
No, I understand that. I understand what's happening there. Okay. Appreciate you explaining it to me.
So did you actually learn something now that you didn't know before or understand before?
Yeah, that apologists are getting more and more desperate as time goes on.
Yeah.
Okay, James learned something. Stream over.
All right, yeah. Thank you and good night. This is a victory for America.
Small victories. Small victories. Oh, anyway. Okay.
I mean, it's just so ridiculous. I don't even think they're going to use that, because if we're measuring like things like, redshift and other factors for how far away something is and determining how long it took the light to get here, like the light leaving there to come to here hasn't made 2 trips. It's made 1. So
that's it. Well, yeah, and they're trying to show that we have uncertainty about how long it took to get here. So, I mean, in any event, if the stars are a fucking billion light years away, it's going to take a billion years unless the light went really fast. I don't understand how Lyle is claiming that light travels faster than the speed of light. I don't know.
You're just making up shit. Like, it's just completely ridiculous. We know, and we talked about this before, where if we have these really high-powered satellites, first we had Hubble, and now we've got James Webb. We got them up there, and we know what kind of a resolution we're going to get. We know which objects are going to come in with which amount of detail based on how far away we know they are. And then so we launch these satellites, we take the images, we process the data, and we get exactly the amount of resolution for ones in different zones that we expected. We expected only this much clarity from an object this far away. We expected this much from another object we know is this far away. It's entirely consistent with that prediction. Like, it's such a nonsensical issue for them to even raise the issue. And honestly, like they're a shame to most Christians who are. It's not just atheists, right? That are shaking their head, going, "Come on, guys!" Right? It's deists, it's progressive Christians, it's moderate Christians. It's just the fundamentalists that are all like, "Hey, look what we came up with," right? everybody else in the world's like, you guys are stupid.
Yeah, and they're still talking about, you know, the idea that we can put somebody on the moon and somebody on Earth and measure light that way, but we still have the problem of causality. Causality takes a certain amount of time over great distances, right? And light limits that causality. So after a while, our stars are going to start to blink out as the universe expands, because things can't get here anymore because we pass that limit of causality. And that's all I know about the fucking physics, because I'm not a fucking physicist.
I remember Neil deGrasse Tyson saying we lose, and it's a very large number, and I can't remember how many, like 10,000 stars per second or something, finally move out of range of our ability to ever see them. Like the light's never going to reach us per second. That's how far and how fast the universe is expanding. So
I decided to give my next life to physics, and I'm going to come back as a 12-year-old who's obsessed with bedazzling named Michelle, and I'm going to devote my life to physics. And so when I die, you guys start the counter, and pretty soon. What in the hell are you guys? I'm getting the water bottle. Zach. God damn it, Zach.
Oh my gosh.
Snack.
Anyway.
There ought to be a cartoon about Snack.
So on to something I know a little bit more about, but not a hell of a lot. Chemistry. So when you see a diagram like this, this shows all the amino acids, James.
Mm-hmm.
What does this diagram do to you emotionally, intellectually, physically?
Well, it makes me think of lemon and lime and blueberry and raspberry.
Makes you want to lick it.
I do. I want to lick it. I'm already licking the monitor.
Did you like have it in the freezer before you started the stream?
You sort of look at it as something that you can't begin to understand, and you just sort of, your mind just sort of clicks off, and you quit looking when you see pictures of molecules.
Right. Normally. Okay. So I'm trying to make sense of it. Like I see non-polar, polar, positive charge, negative charge. So non-polar, I think that it's like a non-polemic. Like it doesn't have it doesn't divide between two opposites. And polar would divide between two opposites. And then positive charge, I'll let you explain it, because I can be completely wrong.
We'll get to that. Okay, but what I'm concentrating on is these diagrams, you know, and people will see those diagrams and are like, nope, not going to even look at that. Not even going to start to decipher that motherfucker, because it's just too fucking crazy, right? So the thing is, okay. So this periodic table of elements, and there's about 100 of them. And
that looks even more delicious. Go ahead.
It does. So on the first row, we have hydrogen on the left, right? Uh-huh. And then we have helium way on the right. And then we've got the important row with lithium, beryllium, boron, carbon, nitrogen, and oxygen, which are really important in biology. And so is hydrogen, right?
What are these listed in order of?
They're listed in order of the number of protons they have and electrons. So carbon has 6 electrons and 6 protons. Okay. Nitrogen has 7. Oxygen has 8. Okay.
All right. Yeah, the periodic table is just like one of the most beautiful arrangements.
Yeah, this is where it all starts.
Yeah.
And all of this is based on quantum mechanics. So when people say, oh, it's the quantum effect, everything is a fucking quantum effect, because chemistry works that way. And what happens here is there are something called these little shells, and they fill up. In the first shell, there are 2 things. So hydrogen and helium fill that first shell up, right? Mm-hmm. And then that leaves, lithium has 1 electron in the second shell and 2 in the first shell. So lithium happens to be highly reactive because it has this electron that really wants to leave the atom, right? So lithium has a bonding of 1 thing, right? You remember, when I showed you these pictures, right, of all these things, you can see that some things are hooked up to 4 things, and some things are hooked up to 2 things, and some are hooked up to 1 thing, right?
Right.
And you'll find that hydrogen is always hooked up to one thing. And you'll find that carbon is always hooked up to 4 things. So look
What's
at
hydrogen
carbon.
always hooked up to? What one thing?
I can't tell you what thing it's always hooked up to because it hooks up to different things. But we'll
okay, but it can only hook up to one thing at a time, is what you're saying.
It can only have one bond. It can only have one string between it and another molecule.
So it's monogamous. But it's the only thing on there that's monogamous.
What's that?
It's the only element that's monogamous?
No. Lithium, sodium, potassium, everything in that row is like monogamous.
Okay.
Everything in that row. Okay. Carbon is really fucked up because it'll hook up to 4 things. And
it's such a slut. I love it. Go ahead.
So what you do, if you divide this table of elements right in half vertically, okay, the things on the left like to give their electrons away. And the things on the right, well, carbon has 4 electrons in that second shell. And it's like, okay, I want to borrow 4 from somebody else. So it wants to get 4 electrons from hydrogen. And so carbon will hook up to 4 hydrogens and steal each of their electrons, right?
Wait, carbon steals from
sort
who?
of, yeah. Yeah, it pulls it in. But I'll show you that a little later. But what I'm trying to show you here is that these vertical columns are really important. Carbon is like silicon. Nitrogen is like phosphorus. You see, I'm looking at the left-hand side in the first row, C, N, O. Okay.
Sure.
Oxygen is like sulfur. Now, the important biochemical molecules are hydrogen, carbon, nitrogen, oxygen, phosphorus, sulfur, sodium, magnesium, and zinc, and iron. Iron is the most common metal. The metals, because they're right in the middle, are a little weird, and we're not going to talk about that. We don't care, okay? But zinc is out here too. So we have iron, and Fe is iron, and then we have zinc, that first row of yellow ones, that sort of thing. But anyway, so that's where we're going. So I just wanted to point out that because of the periodic table and because of quantum mechanics, all you need to know is hydrogen likes 1 thing, carbon likes 4, nitrogen likes 3, oxygen likes 2, sulfur likes 2, phosphorus likes 3. But there are exceptions to that rule, but we don't have to worry about that right now. It gets a little weird as you go further. As the atoms become more complicated and add more protons, things get a little weird, and then we end up with the metals, and they do strange things. But don't worry about any of that. All you really have to worry about is the bonding.
All right.
And I'll show you that. Okay.
Yeah, it's strictly like a numbers game at one level, but then and when you try to visualize what an atom is, they started out with the model of just the tiniest little BB, that you could think of, just one. But then they changed it to where it was like a solar system, and then it was like just a bunch of fuzzy clouds, going around a nucleus.
Right, and fuzzy cloud of probabilities.
Yeah, and it's hard to visualize, but you have so many different models you can use to visualize certain aspects of the atom.
Yeah, we'll get to that.
So the solar system, model is good when you're trying to talk about bonds because it's strictly a numbers thing and a puzzle, putting a puzzle together kind of thing.
So this is where we're going first. This is an amino acid, and I'm going to tell you why. And basically, we're going to figure out what these little lines are and what these little letters are. N, C, O, H, carbon, nitrogen, and oxygen, and hydrogen, right? And what that R means, the variable groups. So that's kind of where we're going, right? But there's some real simple things. Carbon ends up being in that first row, and it's got very few shells, so it has special properties compared to every other fucking atom in that periodic table, every other element. Carbon is what gives us the complexity of life, and that's where the beauty of it all starts, right? So we have carbon, which likes to hook up to 4 things, right? And So what it does is carbon will kind of pull that electron from the hydrogen into, it's already got four things basically around it, and it'll pull one more from the hydrogen basically. So it'll make a nice tight little octet. Because of quantum mechanics, they like to have a full shell, so it has a tendency to pull things toward it, right?
Well,
So that's called
that's
bonding. Go ahead.
All right, so hydrogen doesn't lose what it has; it's now just sharing what it has.
Shares it, right? Yeah. So it's a bond. So there's a bond right there.
A connecting piece, so to speak.
Right. That's a chemical bond.
Okay.
So anyway, so it likes to have four hydrogens around it, right? And that is called methane. And we have methane gas, right? So that's a real simple hydrocarbon. And they call it hydrocarbon, hydrogen carbon, right? So that's what it is. And that's why they do that. So this is methane. Okay.
Okay.
And then we could do things with methane. Like we could take an oxygen atom and put it there, hooked up to the carbon. But now oxygen likes two things, so it hooks up to a hydrogen. And now we have something called methanol, or methyl alcohol, or wood alcohol, which you should never drink, kids.
No.
Never drink that stuff. Makes you go blind for some reason. Okay, so that's methyl alcohol, and that's pretty simple, right?
Uh-huh.
Now, there are other things we can do with carbon. One thing we can do is hook it up to another carbon. Carbon will hook up to another carbon. But then, of course, it's going to want more hydrogens to fill it up and make it a nice, tight, octet. So now it's borrowed more electrons. So that molecule there is called ethane, which we don't use too much, do we? I can't. You don't hear about ethane too much, do you?
I mean, I think buses used to run on it or something.
Did they?
There was some buses that did. I knew a guy that had a bus that ran on ethane.
Are you talking about ethanol?
Well, was that what it was? Ethanol?
No, ethane. Okay. But now if we put an oxygen there and a hydrogen there, now we have ethanol.
Oh, okay.
Ethanol, right?
Oh, okay.
That's ethyl alcohol. And then we can do other things like have another carbon, put hydrogens on there, and we got propane, which are, stoves burn on, right?
Yeah.
Now, if we remove that and put an oxygen there, we have propanol. Okay, but we also could have put, hang on a second, I'm going to delete that. We're going to put a hydrogen there, and we're going to put the OH here because the OH could have been there too, right? And that's called isopropyl alcohol.
How do you have all this memorized?
What's that?
How do you have all this memorized?
I started doing this when I was 10 years old.
Yeah, you do a million of them in chemistry class, and then it's hard to forget.
Yeah, I became fascinated with the combinatorics of carbon chemistry when I was 10 years old because I didn't have any Legos. And I ran out of Lincoln logs, so I started studying chemistry. So, yep. But it isn't that complicated. I just got fascinated with the fact that you can just fucking keep hooking these things up, and you can, like, another neat thing is if you put another carbon here and another and the hydrogens, right? Now we have butane, which we used to light our cigarettes with, and marijuana.
Sure.
So now we have butane. And then we have pentane, which is 5. We could keep going. Hexane, octane. And they get the octane rating from a hydrocarbon called octane. And I forgot the details of it, so I'm never going to try to talk about it. But anyway, octane rating is something you hear about at the gas pump every day when you go to the...
Yeah.
go to the gas. But I mean,
So is that a hydrocarbon that is messing up Ohio from that train derailment? Or
no, that's vinyl chloride, and
okay.
I can show you a picture of that too if you want. But that's actually pretty simple. But now another thing you can do is we can take that oxygen like that, okay, and we could hook up 2 bonds, okay, and then, oh my God, what is it? What is it? Oh no, I forgot. Acetone. Acetone, which you clean your fingernails with, right?
Sure.
Okay, but acetone actually, no, acetone is actually 3. I'm sorry. So what the hell is that one? I'm trying to find the name for that thing, but I can't remember. So acetone actually has 3. I'm sorry, I lied. What is the other one? Let's see. Hang on a second. Why am I not remembering? 3, 2. Oh, let's see. A second. CH. Oh. Okay. Acetaldehyde. I'm sorry. Okay. That's acetaldehyde. And if we were to get rid of 1 carbon and we just had 1 carbon and we had 2 of these things hooked up, we have formaldehyde, which we embalm bodies with, right? So, so if I go back and do that, like that, get rid of 1 of these, because now I have 2 bonds going to the oxygen, right? That's formaldehyde. And you can embalm shit with that. So we have 1, 2, 3, 4 again. We have to count our bonds. Oxygen likes 2 things. Carbon likes 4. We have that. Okay. And then we can do other stuff like this. So we have a hydrogen, and then we have a carbon, and we have that bond like that. And now we can borrow from, well, okay, this is ethanol, right? So we start with ethanol, and I'm not going to draw the hydrogen up there yet, right? So we start with ethanol, and we oxidize it. I'm sorry, I have 2 bonds. I fucked up. So we have ethanol, right? But now we oxidize it. If you leave your wine out too long, you'll end up with acetic acid or vinegar. Does that make sense?
Sure.
Okay. And another way to draw that, the way we kind of like to draw it is like the way I like to draw it is like that, with the oxygen right there. And this little thing right here is called a carboxyl group. So it's often written as COOH, right? COOH, basically carboxyl group. And I forgot something here. Hang on a second. I forgot to erase that. So now we have 4 bonds on the hydrogen again. That's acetic acid. That's vinegar. Okay. Now, an interesting aside is if get rid of that and we put 1, 2, 3, 4, and we have butanol, right? Now I'm going to stop drawing the hydrogens because they do that all the time. You'll see all these diagrams with just, just the C's, and you won't see the hydrogens because people get tired of drawing fucking hydrogens. What you have to know is there's always 4 things hooked up to that carbon. But anyway, so we have butanol here, and if we take and if we oxidize butanol, if we expose it to the atmosphere for a while, we end up with butanoic acid, which is, or butyric acid is, I think, the common name for it. And they got that from butter, because butter, when it smells bad, when it goes rancid, it has butyric acid in it. So butane, the butane, which is just the carbons and the hydrogen, which we use to light our cigarettes, got its name from butter, from butyric acid.
Wait, does that mean that when butter goes bad, it becomes flammable?
No, it's butyric acid, which is not as flammable as butane. Okay.
It also sounds like something you shouldn't consume, right? Like it's gonna do something bad.
Well, not really. It ain't that
No?
bad for you, actually. You break it down in seconds. So anyway, the whole thing that we're heading toward is we have one carbon, and then we have two carbons, and then we have a carboxyl group, which is that acid part, right? Acetic acid. Okay, that's the diagram right there for acetic acid. I haven't drawn the hydrogens. Are you okay with me not drawing the hydrogens?
Yeah, you don't have to draw the hydrogens.
You have to infer the bond, right? Okay.
Sure.
Okay. But now, if nitrogen likes to bond to three things, like three hydrogens, that's ammonia. Okay.
Oh.
Nitrogen and three hydrogens is ammonia. Okay. But we can also bond nitrogen to carbon and have two H's out here. Okay. And now we have our very first amino acid. So that is the basis of all proteins. This thing is called glycine. So it's the simplest amino acid. Okay.
Okay.
Okay. And this is an amino group, and this is a carboxylic acid group. So we call it an amino acid. Okay, and it has two carbons. So does that make sense?
Yeah, it does. So if you take some hydrogen and some carbon and some just various other elements, you just mix them all up in a can. What determines what things bond to what? If there's multiple possible bonding variables,
you're gonna, depending on how much heat you apply and depending on the acidic conditions, all the other chemicals in it, you're going to end up with a whole bunch of different compounds. You're not just going to end up with glycine. You're going to end up with carbon dioxide and carbon monoxide, and you're going to end up with ethane and maybe some methane, or as the Brits like to say, methane. I hate them for that.
All right.
Anyway, but no, it's not that simple. In order to get an amino acid, it takes a little bit of the right conditions in order to get them to hook up the way they hook up. But we're not going to talk about abiogenesis. We're just talking about evolution as it is, from bacteria onward, right? So that's what we're interested in.
Yeah, that makes sense.
So anyway, so going back to this PowerPoint, you can see right there that we have the carboxyl group, the amino group or amine group, and we have the carbon and the hydrogen, and then down here we have the variable group. So that one varies across all 20 amino acids. If the R is equal to H, then it's a glycine. Then it's the simplest amino acid. So now if you look at this, you can begin to see what the hell's going on here. The things that are highlighted in they're colored or in green or yellow or blue or purple. The things that are shaded in, those are the R groups, and those are how the amino acids differ. So, okay. So now you can look at this and say, oh, so let's look at cysteine. So we have the basic, we have the N on the left, right? The NH2. And then we've got the carbon, and we got another carbon with the carboxylic acid, but then going downwards, we have another carbon, and then we have a sulfur and a hydrogen. Sulfur likes to hook up to two things like oxygen. So now we have cysteine, which is really an important molecule for zinc fingers. So, and then you go look at the other one. Proline is a little weird because it's got that ring. You can form rings with these complicated structures, but valine is hooked up to one carbon, and that carbon's hooked up to two carbons. Okay. Mm-hmm. Going back, we need to go here first of all, and I need to explain that. Oh my goodness, that was not the right scribble. Okay, not drawing the hydrogens, right? We can have carbon, 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 and then we could have another carbon here, And that could hook up to 2 carbons here. And this one could hook up to another carbon. And that one could hook up to 2 carbons. So you can see now when you have gasoline or petroleum products, you get real complicated things like that with lots of carbons hooked up in really weird ways. You can put another carbon. So you can see how the complexity, this is the secret to life. The complexity of this the way carbon hooks up in many, many different ways, right? They're called isomers if you have the same number of carbon atoms and you have a slightly different way of hooking them up. So anyway,
yeah.
So and you can see that over here on looking over, reading from the top: glycine, alanine, valine. Valine has carbon hooked up to 2 other carbons. You see that little triangle thing that's shaded in yellow?
I'm looking for it. Hold on. Where am I looking?
Okay, start on the top row. The first one is glycine, alanine, and then valine.
Valine, okay.
Okay, look right above the valine that's written out, and you'll see a 3 carbon, kind of like a triangle.
Sure.
1 carbon hooked up to 2 carbons, right?
Okay.
So that is very simply one of these deals where you've got your basic amino acid structure. Oh shit. Okay, a little too happy. I'm getting too happy. NH2. We'll just put an NH2 there instead of drawing that out. We have an OH there. Okay. And then we have this middle carbon hooked up to C. And then that goes like that and hooks up to 2 more C's. That's a valine, right?
So what stops one of the other C's from just like bending over and giving some of the C's that's not connected to a connection, like a reach around? Like, what's to stop them from all just like bundling into this like nest of C's?
Quantum
what stops quantum mechanics? Okay,
we'll get there. We'll get
all
there.
right.
But you can see proline does that. You see that? The next one over, cysteine, proline on the top row. You see how it bundles, how it folds over?
Yeah.
So yeah, it can do that. Okay, so because it's long enough to reach around. But the thing is, there's something else that you have to know about molecules and quantum mechanics, and that is that there are certain shapes that these things can adopt. Like carbon likes to have a tetrahedral. It likes to have a tetrahedral shape to it, right? Okay. When you bend those bonds, it takes energy. They like to snap back into a certain angle. So that's why they don't all just reach around and start mixing up. Okay, right. They have certain constraints. And that's going to become really important. I'm trying to see if we got any other stereochemistry here. Let's see if I can. Let's see.
So, how come Jesus made it that way?
I don't know why Jesus did that. He's kind of cool, right? He was like designing Legos for life, right?
That's fair. Okay. I mean, you got to have a hobby. If you exist forever, you got to do something.
Right. Like, I don't know. I don't know what that is. Chegg. Okay, so that just shows you how they hook up. They have certain angles that they prefer, right? And they can rotate around those angles, but they can't bend so much. And there's just, and this is a quantum mechanic picture. Like you see those little egg-shaped things, basically.
Right.
You calculate those with quantum mechanics, basically. You come up with all these different bondings and bond angles and things like that.
I mean, that makes sense. And it's relatable because we all have angles we prefer and certain angles we just can't get into. We try, we stretch, we bend, we try, we pull a muscle, we stop. Right.
Yeah. Okay, so now the interesting thing about this, okay, these where are we here? Let me get rid of that for a moment. Okay, so I'm gonna try to make this a little smaller. And I like a clean board. Oh, got a little dot down there. Okay, so we got the C, we got the OH like that, and we got the double O up here, and then we're going to put our NH2 right here, and that's an amino acid. Right? And then we have something down here, something. We don't know what it is, right? Something. Okay.
Sure.
And now over here we have another NH2. We have a C, an OH, and we have a double O like that, right?
That's what we had before, isn't it?
We have two of them, right? And we have, so these are two different amino acids, right? We have something down here. We don't know what it is. We don't know which amino acid we have. Oh, well, fuck it. Let's get real. Okay. So this one is just a hydrogen. So that's a glycine. Okay. So we're not going to draw anything there, but this one is a valine. Okay. So we have valine and it's a V and this is a G like that. And what we do here is we're going to take an H from there, and we're going to take an OH from there. So we're going to take an OH from that one and an H from that one. Then we're going to link it together. Hang on a second. Whoops. Fuck. I'm not the best artist here. Okay. We're going to link it together like that, right? And now we have one H left over. And right here we have H2O. So we take water out of that bond, and now we've hooked glycine up to valine. So we have the beginning of proteins. You see?
Wow. Yeah.
So now these two things are hooked up, so we have a very tiny little protein, which is called a peptide if it has less than 50 amino acids. Peptides are just proteins that are have very few amino acids. So we have a peptide. And you'll see all these protein diagrams that go G, V, V, G, and we can have an R. And of course, those things are all right here. Right there. See?
Yeah.
My diagram, you see the G, the A, the V, the C for cysteine, P for proline. First table is real simple. Second table, we're starting out good. Leucine, isoleucine, methionine. Oh, tryptophan. Oh, no. It's a W. I don't know, because they kind of think it looks like a W, so they named it W. So anyway, when you see those weird amino acid charts drawn out like that, what you're seeing is just these. It tells you what the sequence of amino acid, because we can keep repeating this process of hooking things up over and over and over again, right? Like this. We can just keep hooking, like we take that one, combine it with another, the carboxyl end of another one. Okay, and this is called the C terminal end for C terminal end of the protein, and this is called the N terminal end. So when we say words like that and you think, okay, I'm going to tune away from Speed's channel, he's talking about terminal ends. Now you know what the fuck I mean, right?
Yeah.
So every protein has a C terminal end and it has an N terminal end. Now, but here's the cool part, and I wish I could bring the pictures in, but okay, let's go back to this. So basically, we've got an NCC, right? That's one amino acid, and we got an NCC, and we got an N. So it just keeps repeating that backbone over and over and over again. And of course, there's things hooked up here that make it a unique kind of complicated thing. But we're going to talk about magnetic balls in a minute. Okay. So you've got that. And what you have here is between this bond right here,
Mm-hmm.
they named that psi, psi, the Greek psi letter, right? Psi,
Mm-hmm.
like that. Psi. So that one right there. This one they named phi, sci-fi. So it's sci-fi.
Nice. So if
Yeah.
we're gonna do that, then you need to write and over all that, 1701-D.
Okay.
You just have to write it. If it's gonna be sci-fi, you have to write that. 1701-D.
Why? I don't get the reference.
Google it.
Oh, okay.
NCC 1701-D.
Okay. Anyway, so those bond angles, like they can rotate, like around this bond. This thing can rotate. So these amino acids and these proteins end up having a certain shape depending on how they rotate, right?
Mm-hmm.
So they can rotate in different ways. I'm trying to find an example. Let's look at protein folding. Protein. And this is what makes the magic of life possible. This, let's see if the Wikipedia has anything on it. Yeah, I guess we could look at the Wikipedia. I don't know. Anyway, okay, the Wikipedia has like these ribbons that you see. They're called alpha helices. What those are is 3 to 10 amino acids or more that are all kind of folded in a coil. And there's a reason why they do that. And I'm going to kind of get to that next, I think. So let's talk about that. If you have an oxygen, right, and you have 2 hydrogens, okay, the oxygen has 8 protons. It's one hungry motherfucking magnet. Protons are positive. So it's got a positive pole. And it's got 8 of them. Poor little hydrogen out here only has 1. So this sucker is going to pull the electron from hydrogen close to it, right?
Mm-hmm.
And it's going to end up becoming negative, like a negative end of a magnet. And this is going to be a positive end of a magnet, right?
Mm-hmm.
So now what happens is if you got water, which if you fill your glass all the way up, you'll notice that it kind of like lenses at the top. That water is kind of sticky. It kind of sticks to each other a little bit. And the reason for that is because of that magnetism. Okay.
Right.
We got a negative magnet here and we got a positive magnet there. And it sticks together. And if you look at these suckers, let me turn this on for just a minute. What just happened? Somebody just drew something. These little suckers are little magnetic marbles, right? They don't stick to each other too well. What the fuck? Oh, what is that?
It's registry number for the Star Trek Enterprise.
Is it really?
Yeah.
I didn't know that reference. Well,
yeah. The original Starship Enterprise from the original series was NCC-1701-D, and then they proceeded to crash it at least twice, 3 times, given the series too.
Those the Next Generation kept crashing ships. That was their thing.
Yeah.
Oh, lost another one.
My marbles. Anyway, these marbles aren't strong enough to show you but they're magnetic. They repel and they kind of stick to each other.
Yeah.
You draw them out a little bit, that sort of thing. Anyway, atoms do that. And because atoms do that, that's why proteins stick to each other. It's that simple.
Nice.
Yeah.
I think I would like to buy some of those magnetic balls.
Oh, I got a whole bunch of different kinds. I've got these really wonderful little tiny metal ones, that are made of really strong magnets. I'd have to get up and go get them, but I'm not going to do that. But anyway, so you have this stickiness, right? And the result is that when you have a long chain of amino acids, it'll sometimes form, like a spiral, and that's an alpha helix. And then it'll go out here and it'll do like nothing for a while. And then it'll go out here and it'll form something called a beta sheet. which is almost like a little, they show them as, if you look at the wiki, where is it? PPT, Chromo. Okay, you see those big fat ribbons down there that kind of like have like arrows? Well, let's go here. Okay. You see those purple ribbons on the bottom that have arrows on the end of them? Those are beta sheets. And then you have alpha helices. And anyway, because of that R group, that where are we here? PPT, good time. Okay. Because of we have C, C, N, and C, C. On each of these, we have something different, right? We might have a hydrogen and or a carbon, a hydrogen, and a sulfur atom. And every one is going to be a little bit different. So these groups right here define the way that this thing sticks to itself. And every protein has one or more ways that it wants to fold up, and it forms these little molecular machines that the creationists love to talk about the machines, but they're a lot more fluid than that. But anyway, it's because of the stickiness of these molecules. They, like this will bend over and stick to that, right? Or this will bend over and stick to that in various ways. And then we have DNA, and DNA, like proteins, can stick to DNA in various parts. And of course, we have the ACTG, right? And each one of these is a very similar molecule that has different properties, and it will stick to different kinds of proteins. So now we have proteins that stick onto the DNA and modify what kinds of translation to proteins we can get out of it. So have we, are you following?
Yep.
Why? I thought you couldn't.
I don't know. But, this is all good. And didn't they recently figure out something about protein folding that they couldn't figure out before? Wasn't that
how to do it with a computer.
So now they understand what makes proteins fold the way that they do because computers help solve it?
No, they've known that since 1960, 1970 is when 1950 is when they first did hemoglobin, and they figured out how proteins fold up. But they couldn't solve it because of the math. By the time you get to all these different, the creationists want you to believe that it's like Legos where they fit together in a certain way. Mm-hmm. It's not like Legos. It's like magnetic balls. They can fit together in one way, or if you add some energy, they'll be a little bit different. It's a lot more fluid than that. And a protein does not necessarily have to lock and key fit into another one, though oftentimes it does. Sometimes it fits less well than other times. Sometimes it doesn't stick at all. They, repel or whatever. Mm-hmm. So it's not like the creationists want you to believe.
To me, it sounds like the creationists have trouble with the idea of fluidity and all its connotations.
Yeah, they do.
It doesn't surprise me. Their thought processes are very simplistic and rigid.
Yep.
So they picture certain things in their mind based on words that they read, but that's not what the words are meant to convey. And so they got these ideas in their head about how it must work based on what they imagined, right?
Yep. So now we're on the zinc fingers. So what the hell is a zinc finger? So we kind of know that proteins, are these things that stick, that bend around by those five side bonds, right? Within certain constraints, you can only bend them so far, and they're going to want to snap back, into something. They're going to bend around, and because they magnetically stick to each other, we might end up with, like you got a protein chain here, right? Protein chain coming down, and it kind of folds around, and that one likes to stick to that one because there's a little magnetic influence there, right? So it'll kind of stick together. Well, the other thing that things like cysteine and histidine do, if you have two of them, is they can trap an ion, a metal ion, which is a zinc plus plus in between them. So they kind of trap it, right? So now we have a protein folding around, and we have a cysteine here, and we have two histidines here, okay? And they trap a zinc right in the middle of them, okay? And they form this kind of like bulging thing, which becomes the knuckle of one finger. So we're going to draw a little. No, we can't. You can't do a fingernail. So okay, so that's a knuckle of one finger, and then it goes around, and there's another histidine, and
it does it again and creates another one, right?
And it creates another knuckle, right? And so that grabs a little zinc thing, and it folds around like that, and it creates another knuckle. Okay. Well, these knuckles, okay, the DNA helix. I don't know how to draw a helix, but anyway, these knuckles fit into, like, one zinc finger knuckle will fit into the groove of that DNA, another will fit into the groove of that DNA, and another will fit into that groove. And so if we have three of these knuckles, and these proteins out here have a particular magnetic properties that match the grooves here, they're going to lock into that DNA.
Yeah.
They're going to, like, in some cases, if they have other things attached to this cysteine out here, it could prevent that DNA from expressing that gene. So now that gene has been inhibited, basically, by a zinc finger or three zinc knuckles sticking into it. And what they're doing now in medicine is they're designing these knuckles to fit into a certain part of your DNA so that they can alter certain cancerous mutations that are causing problems. And so they're creating these designer zinc fingers that can actually be medicine for you. They can start to pick and choose what genes your cells express. And that's what zinc fingers do.
Wow. Well, that's pretty fascinating.
It is. Some designer stuff. And here's a, kind of a cartoon depiction of a zinc finger. God, PowerPoint sucks. With the two histidines and the cysteines. And here's a more molecule-like looking thing showing the knuckle out here. Of course, you can't see my cursor. And let's see, what else do we have? Here is a picture of like the details of how the pieces of the zinc finger lock into a particular kind of DNA. This is from a paper where they're doing designer drugs, and they're creating designer zinc fingers to modify things. So
wow. So don't they worry that these zinc fingers are going to get lodged in places they didn't intend for them to get lodged in?
Oh, they have to. That's why we like to test on rats first, and before we do humans.
Fair.
Yeah, and they're having a hell of a time with this because it turns out it's not quite as simple as they thought, because it's not like a machine. It's like it's more like a chaotic system in weather, where the influences of one different amino acid are going to have a surprising result as to what locks in and what doesn't. And they're also going to find that some things lock in more, like a little bit, some things lock in a median amount, and some things lock in really well. But they're having trouble predicting the mathematics of doing that. They're making a lot of progress, and it's a real hot field of research right now.
Wow.
So it's a big thing. What else we got on zinc fingers? There's some quantum mechanics. Those little weird looking egg and bell-shaped things on the bottom. That's basically, every atom has a characteristic shape that's a lot more complicated than they imply in grade school. And quantum mechanics is what determines the angle that those bonds can have, how the molecules can move around, things like that. What else do I have there? These are the different kinds of zinc fingers. There's a C2, two cysteines and two histidines, something called a gag knuckle and a treble clef and a zinc ribbon, and there's a whole bunch of we have 700 of these zinc finger proteins in our invertebrates.
Wow.
In our genome, and they think that the evolutionary pressure that created them was because they can repress DNA. When endogenous retroviruses jumped around in our genome and inserted crap into our genes, like they inserted some bad genes, a zinc finger, because we had so many of them being created, and I can tell you a little bit about how they create. We had a library of zinc fingers. One zinc finger would repress that son of a bitch, and if it didn't, of course, the embryo would die before it got born, and natural selection would cut it out. But if we had a zinc finger in the library that could stop that endogenous retrovirus from killing us, then it would lock in and prevent it. So we end up with, now all of a sudden we have a zinc finger and we have a retrovirus in the genome of the entire population. And if you lose one or the other, you're going to die. Okay, so both of them are conserved. Well, no, actually, if you lose the zinc finger, you're going to die. If you lost the ERV, you might be okay. But anyway, so we end up with all this junk that's involved. We end up with zinc fingers that do something that are very important for you to stay alive. But the reason they're there is because there was some junk that they had to shut off. So zinc fingers do a lot of that, and they do a whole lot more.
Wow.
And as it turned out, okay, so what happens is, let's get on here. Okay, we have a cysteine. Oh God, I can't draw with that. We have a cysteine, and I think
I wish it could, because those are really cool looking colors, the neon stuff. I like it.
Right. And we have we have a whole bunch of stuff that ends up being the knuckle, and then we have two more histines out here, and an X and an H, and then we have some more stuff, amino acids. That the X's mean that the amino acid doesn't make a difference. But anyway, so we have this repeating pattern that's usually about 28 units around there, 28 amino acids, and we have the important part. And what happens is these things can fuck up in early bacteria 3 billion years ago, and the DNA becomes confused and it creates two of them. So now we have two that are identical back to back, right?
Mm-hmm.
And Cell will show this big table, and he'll show you how the histines are highly conserved. So we have this repeating unit. Well, then, because it repeated once, it's really easy to slip up and repeat again when DNA is trying to replicate. So anyway, proteins tend to, like with these repeated sequence, tend to grow and grow and grow. And then what happens is these things mutate on some, like the whole gene could become duplicated, and then some of them will mutate, and they will lock, the knuckle will be different. It'll lock into a different piece of DNA. And so now we have a library of these things developing, because genes will get duplicated, and sections of genes will get duplicated, and chromosomes will get duplicated. And as life evolved, we ended up with this library of 700 zinc fingers that turned out to be really useful for picking out a piece of DNA and shutting it off or turning it on or whatever. Usually shuts it off, depending on what kind of zinc finger you have. But anyway, questions on zinc fingers?
No. Now I understand how it's relevant to the discussion about evolution. And holy shit, man.
Did you fucking learn something?
Yeah, I did. Like, I learned a lot. I didn't understand how things connect and how they bend and they shape, and the limits of that, and how that completely creates different chemicals and different interactivities and connections and blah. That's freaking wonderful, honestly.
Cool. My job is done. I'm taking down my channel today.
I'm sure Sal would probably be pretty happy about that.
Yeah, I don't think there's anything left on my bucket list.
Yeah, but I'll tell you, no mention of Godell's incompleteness there.
That's right. We did not need that. It's just not important.
We don't
anyway.
need to know it. Yeah. That's awesome.
Okay.
Well, thank you for that introductory lesson to molecular chemistry.
Here's what I'd like you to do. When you see a diagram of a molecule, start looking at the letters and look at how they're hooked up just a little bit and get an idea. Like go and look up aspirin on the Wikipedia. And well, let's do it. Let's fucking do it.
I'll start paying more attention. I'll notice like hydrogen will only connect to one thing, and
or you can enroll in a college chemistry class.
Yeah, I could do it.
Oh God, they run you through so many details, and
you know what you need to do? Go through some of Professor Dave's videos. Just go to his channel and type in chemistry, and he'll probably have zillions of relevant videos for you to go through.
Yeah, he gets a little deep. So here we go. Aspirin, Wikipedia, right? Like when they give you a drug, you always go to the Wikipedia and you take a look at the chemical structure of that thing.
Yes.
And oh my goodness, why is that? Is that the one? Not the one I wanted to look at? Yeah, that's it. But why is it clicked? Okay. Let's try to make it. Can we do it this way? I don't know. Not doing it that way. Oh, there we go. Okay, you see, there's that carboxylic acid group up there, that C. Oh, the other thing, they will often leave out the C's and just put, can you see my cursor? You can't. God damn it.
No, but...
Okay, on top, you see the O double bonded. You see where they all intersect. There's a carbon atom there. That's the thing I forgot to tell you about diagrams. Sometimes we always leave out the hydrogen, almost always. Sometimes they leave out the carbon and they just draw the diagram. That's important to know. And let's see, cool. So let's show you that, just so it isn't confusing. I can draw C, or I can draw like this. Whoops. Like that. Okay. Another C. Draw it like that. And then I could basically draw another C here. So there's an implied C at the vertex. And like that. And now we have a ring.
Well, that works better for today. It's Valentine's Day, so we'll go with that one.
Oh, yeah. Okay. That works good. Or you could have something.
By the way. Sorry. Yeah. Esther from the for Atheist, today's her birthday.
Oh, Valentine's Day. How about that?
Yep.
Okay. So we have a C, and we have a double bond, and we have a C, and we have a C, and we have a C, and we have another C, another C, another C, and every other one becomes a double bond. That's hexane. Or what is that hexane? Cyclohexane. So that's called cyclohexane. Or benzene.
Is it cyclo because it makes a circle?
Yep, cyclo because it makes a circle.
Nice.
Or another word for it is benzene. And isn't benzene pretty common? What do we use benzene for? I forget.
Oh.
Anyway, that's benzene. So another way to draw that is like this.
We use benzene to make poisonous rings of gas and stuff.
It's called a benzene ring. But this is another way to draw it. You'll see that over and over in molecules. You see it up here. The interesting thing is these double bonds rotate around. They have like a resonance. They don't just stay in one spot. They can interchange. So benzene has some unique properties, but because of that. But anyway, so it's drawn that way without the carbons. Okay, and that's what we're looking at.
Randolph wants to congratulate you for drawing a beautiful cake with chemistry.
Nice.
There you go. Anyway, aspirin is pretty simple. It's got that structure right there. And
I love to say acetylsalicylic acid.
yeah. And if you go look up, let's see, let's look up something else here. Where the
I
hell?
try to imagine Daffy Duck trying to say it. That's just a little bit of my internal life. I thought I'd just kind of share with everybody.
Mm-hmm.
Diazepam or Valium, and here's the structure of that. It just shows, there's carbons at every vertex. There's a chlorine. You'll often find I hate when they give me a drug that has chlorine in it, because I don't like chlorine, but it has a lot of pharmaceuticals have chlorine in it. But it's got some nitrogens hooked up in that ring, and it's got, double bonded oxygen. And every one of them is simple. And then it has this little structure down here, which shows you a little bit of the stereochemistry of Valium or diazepam. So when the doctor gives you something, you look it up on the wiki, you look at the molecular structure, and you look a little bit and try to think about what's in it. We have 1, 2, 3, 4, 5, 6, how many carbons it has. Down here, of course, it conveniently tells you how many carbons. No, maybe. I lied. They don't. Why don't they? Oh, right here. C16, H13, down on the bottom right. That sort of thing.
Right.
Anyway, it's a good idea to kind of get through. And the neat thing about it is the reason we're here is because of that complexity, because of this Lego building block ability of, chemistry to build up. And anyway, that's enough. That's enough.
Well, thank you for this.
Yeah. Well, I hope it helped.
It did. It opened my mind to a whole new realm of how the universe works.
Yeah, and a little bit of understanding of evolution and how, there's all these changes, like all of these different proteins get created, and a lot of them are neutral. They like to use that word. That means they don't have any effect at all. And then eventually they'll lock into they'll bump into another protein that they stick to, and it will have an effect on your cell. And that effect on your cell may be that you burn glucose just a little more efficiently. And that thing may end up getting into your entire population. And now we have an evolutionary change. And
yeah.
So it all just pops up. Anyway, what else is going on in the that after show you had last night with Derek, where he was talking about the religious myths of things that basically godlike beings on earth that had godfathers, or their father was a god. The myths that Derek was talking about.
Yeah,
Right,
just about all of them.
He called it topos, or what was it, a meme?
Topos are type. We kind of get the idea of meme or whatever from it, but I think the idea was a type or a trope. Yeah.
Trope. Yeah, and topos would be form. So it's a certain form of story. And it turns out that form of writing was really popular back then.
Yeah, we saw I saw The Northman with a friend, and we both agreed that there was a little bit something off about that movie because it didn't follow the usual hero kind of format that we're used to in these movies. Like there's a setup, there's a struggle, and there's an act of redemption or resolution to it. And it usually at the end, somebody walks away with somebody else in the sunset, and things are happy, or there's hope for a future.
Or there's a new season.
The Northman was a movie.
Oh, okay.
So, or there's a new season. Yes, it's open for a new season. But it was the ending. We're not used to tragedies in the cinema, actual true tragedies, and it took more the form of a tragedy of the the, if you seek revenge, you might as well you need to dig 2 graves, one for the other person and one for yourself. It was kind of along those lines. And that's just not one of our major tropes or types of movie. And thus it leaves some sort of discomfort or a sense that this isn't a good movie, because it doesn't follow the usual pattern. It's not to say it's not art, but people will come away, and I did hear people talk about it as being a bad movie when it was just a tragedy type of story, and that's what those to me that's what those types do in these literary works. Is it provides a framework that is both familiar and strange at the same time to the reader. So they'll give it the time of day. It'll provide some sort of sense of satisfaction for having gone through. And nobody likes to go into totally new and different territory all at once. And those tropes kind of provide a this is a good story kind of reassurance to people. That's just my thoughts about it anyway.
So the Northmen?
The Northmen, yeah. With one of the many Skarsgård
oh my
actors. God. And then that cute girl who was also in the menu.
Okay.
Here recently.
Oh, I made a mistake.
Girl in the menu, huh?
I made a mistake, and it's going to bug me forever, but cyclohexane looks like that without the double bonds. I'm sorry. What I did the double bonds was benzene. So anyway.
Cancel speed.
Cancel speed. I'm going to let it
Cancel
go now.
Speed.
I'm letting it go. Okay.
It's really interesting to study the kind of literary formats that moved people in different generations, and that's essentially what they're doing. They move people, and they also add legitimacy to the story you're telling.
Hot off the press, we got Randolph Richardson is on the Theist Helpline show. I'll be presenting a new idea created on an omni characteristic that the Christian God should have that seems to be missing. So,
interesting.
Do you have a link to that yet? Randolph? We need a link. That would be great. Cool. So let me see if I can copy that. I'm going to put that in our description.
Yeah, I'm going to go and hit the notify me thing right now.
Yeah. Cool. So
oops, sorry.
Let me go and pop that up and put it down here and show it.
So I think in the future, for James's sake, we need to, instead of having the zinc finger flipping you off, it needs to be a friendly wave.
Oh yeah, So somebody thought there was going to be some kind of controversy. Who was that?
Good. That brings more people in, saying, "Yeah, let that James guy have it."
I think that was Icarus. Either Icarus or Wooly.
Lately. Yeah. Oh, I have been pissing off some atheists lately, so I know a lot of people will be like, "Yeah, show up for that."
So have you put the link in the description yet?
I'm working on it.
Okay.
It's an omni trait that the Christian God is missing. Now, I know he has some that they don't normally mention, like omni psychopathy, omni assholery.
Okay, it's in the description. We got it. Yep. Cool.
Omni non-existence.
Yep.
He doesn't exist everywhere.
We haven't been live since the Brazilian douche canoe came on our channel and got a moderator or a wrench. And Stephanie Helms basically brought me into the principal's office and schooled me on that shit.
Wow.
So Otangelo is he can come into our chat. He ain't going to come into the show. He doesn't know how to do an apology. He's an asshole. He did a horrible fucking thing. He never felt any remorse for it, and fuck him. Basically, that's our position on that.
Uh-huh.
Did I say Otangelo? I meant Brazilian douche canoe.
BDC
Right.
for short.
Yeah, Brazilian douche canoe. So that happened, and
When did that happen?
last time we were live a couple days ago, I think.
So
The
the douche canoe, formerly known as Otangelo.
Yeah.
There you go.
Gotcha.
Yeah, he came in with some kind of bullshit, but you atheists still entertaining your atheism fairy tale or some fucking thing and some other bullshit.
My atheism
And
fairy tale.
Otangelo has always been our clown, and he is a fucking clown with his Shroud of Turin crap, and he's not only a clown, but he happens to harbor the usual fundamentalist fucking ideas that are causing a lot of goddamn problems for trans people and LGBTQ. The whole fucking group is they will shit on them, they'll fuck them, they might even kill them. They're that rotten about it. They're just rotten in their hearts about this stuff. And time had passed, and Otangelo did a couple half-assed apologies, and I was very guilty in my tendency to hand wave it away. And I'm going to try not to hand wave away those kinds of atrocities anymore, because that's wrong too, right? Standing by and just fucking allowing it,
Here also is the thing with me. Let's say instead of the internet, we were all at the food court of a big mall. All of us, the people in the side chat and us in the panel, just gathered around a table or all sitting at one big table. And then somebody like Otangelo comes in right in the middle of the conversation and goes, you atheists have no basis for morality and life.
Right.
And we were talking about something else. That would be considered antisocial behavior. And people like Otangelo, BDC, our Brazilian douche canoe, they don't interact like people. They interact like bad performance artists who they just want to get a reaction. They want to stir the pot. They want to throw a firecracker in the middle of the table.
Well, everybody knows this. You're sitting around watching TV on a Sunday afternoon. There's a knock on the door, and they hand you a watchtower. And it has nothing to do with what you were doing. It's preaching, and evangelizing and all that bullshit.
Ironically, the JWs never knock on my door. They haven't in decades. And I would welcome that shit. I'd be like, yeah, come on, let's have that discussion.
They haven't come here since the last time they came here. Okay, there was a car parked in the yard. Two trembling, a little boy and a girl, about 9 years old, around that neighborhood, trembling, handed me a watchtower and asked if I wanted to talk about some fucking thing. And they were shaking. Those poor little kids were shaking. And the parents sat in the car.
Jeez.
And I don't understand what kind of parents would do that to their children. Send them up to a strange, quirky looking old man with fucking hair sticking out of his head like I have, and fucking let their kids fucking approach the door. What is wrong with them? And that was the last time they ever showed up. They never came back. I don't know why. I used to have them over all the time here, and we'd have long discussions about how lions don't eat grass. Because their idea of heaven, is everybody's going to be eating grass, and and
it would be heaven if they were smoking it instead of eating it.
Yeah, it was kind of fucked up.
Sure. So Neil has a follow-up from his debate this afternoon. I think I might go live for an hour to do my review of it before he does his.
Oh, good. Will you
So-
please put a link? Will somebody give me a link to the debate?
Oh, the debate from last night. Yeah,
Yeah,
somebody
'cause I don't
probably
even know
grabbed
what
that.
channel it was on.
Well, Gnostic Informant, so
Oh, it's Gnostic Informant.
yeah.
Had that at the beginning. Son of a bitch. Oh, let's see. Gnostic Informant.
Well, I'll tell you what, the reading that Neil and of course Derek Lambert have done over the last few years, just to host their channel, is amazing.
I know. He knows so goddamn much.
Yeah.
Pretty incredible.
Yeah, I've gotten like 3 or 4 pages read of that Robin, is it Robin Faith Walsh?
Yeah.
Yeah, of her book, and I just, it's hard to find the time to get it all read that I
What was
want to
the
read.
book he recommended last night?
I
I
don't know.
recommended several books. Derek did.
Well, one of them was the
one.
Satyrion or something like that.
The Topos one?
Well,
One
there's I don't know. He recommended all sorts of books. I asked him at one point for a list, but I guess if we go to Derek's Amazon page, it would be there. Or I don't know if Neil has one too. I took a picture, I think, of my screen.
That's the kind of book I like a lot. Okay, I'm going to link this debate in my description just to have
I didn't take one with my
copy video.
screenshot. Dang.
Video Earl. Okay, I want to shoot it ahead now, guys. So you're going to have a thing later today, James? Do you know what time?
I'll probably schedule it 10 minutes from now.
Oh, okay, so soon. Okay. Well, let's do
Yeah,
that.
because I can't wait because Neil's going to do his, and I want to get mine in first before he does his. So,
I see how you are.
that's how I am.
I see how you roll. Okay. Okay, guys, we're going to shoot it ahead then.
All right, guys. Thank you so much.
I feel pretty good about having taught you something. So
Yeah. I plan on showing off in the near future with all the new stuff I've learned.
I feel good about the flashlight picture.
Yeah,
I liked it.
Yeah, excellent. That was the highlight, Scott. That was the highlight of the stream.
I was sweating when I drew it because I'm no artist. I was just sweating. It's like I want James to know this stuff.
Yeah, and I want to apologize to everybody in chat when I'm doing what I'm doing with multiple windows and stuff like that. I'm sorry I didn't read the chat, but I have saved the chat and I will try to review it. I really apologize for not if I missed anything out there that I should not have missed. So,
Right.
okay, shooting her in the head. Goodbye, cruel world.
Goodbye, crew.